Since the previous topic established that enantiomers are different compounds, it would make sense that different compounds have different names. And indeed, UPAC nomenclature defines different names for two enantiomers according to a system of a few relatively simple rules. If we look at two chiral molecules, two chiral enantiomers of each other, such as these two isomers of alanine, which is a naturally occurring amino acid, and what we say they differ in is their configuration. In other words, the stereochemical relationship of substituents around the central carbon. And unlike conformation, which can be changed through rotations or ring flips in cyclic compounds, configuration cannot be changed without breaking chemical bonds. Now, to name the enantiomers, we use the so-called Kahn-Ingold-Prelog rules, which are named after three chemists that established this nomenclature. And this nomenclature assigns the so-called R or S name to each chiral carbon, and then appends those names to the beginning of the molecule's name to indicate chirality. To assign names through using Kahn-Ingold-Prelog rules, we follow two simple rules which have certain sub-rules. And so the first rule states that we should assign priorities, we'll see what that is in a minute, to substituents. In other words, we'll have a chiral carbon with 4 different substituents, and we will rank these substituents in priority from 1 to 4. And the first sub-rule, well, the question is, well, how do we assign these priorities? And the first sub-rule tells us that higher atomic weight indicates higher priority. So let's look at a simple system where we have fluorine, hydrogen, chlorine, and bromine attached to the same carbon. Here we would assign priority number 1 to bromine because it's the heaviest element, priority number 2 to chlorine, and fluorine, and then hydrogen. If we replace, for example, bromine here with a carbon, the CH3 group, then priorities would change. Now chlorine would go number 1, fluorine would be number 2, carbon, because it's lighter than fluorine, would be number 3, and then hydrogen would be number 4. Okay? Well, but now the question is, that is answered by the second sub-rule, is what if we have a tie? If two substituents are both carbon-based. So if two substituents are tied, then we keep going down the chain, comparing not the directly attached, but the second, third, and so forth, until we encounter the first point of difference. First point of difference. For example, if we have now substituents such as CH3 group, C, bromine, chlorine, and an ethyl group, clearly bromine will be number 1 and chlorine will be number 2. But between carbon-based methyl and ethyl groups, ethyl group will have position 3 and methyl group will have position 4, because the carbon of the ethyl group is attached to 2 hydrogens and 1 more carbon. So this carbon has a higher molecular mass than any of the 3 hydrogens that are attached directly to here. In other words, the longer, it's a good rule of thumb that the longer and more branch substituents get higher priorities using this system. So if we have now a bit of an extreme system where we have hydrogen here, CH ethyl group here, and then isopropyl group here, this will be priority 1, this will be priority 2, and this will be priority 3. Because here our carbon is attached to 2 more carbons and a hydrogen. In this case, carbon is attached to 1 more carbon and 2 hydrogens. And in this case, carbon is attached to 3 hydrogens. And even though all 3 of them are carbons, the first point of difference between methyl and both of these encounters immediately because these hydrogens are all lighter than the carbon. And then we need to look for the second carbon substituent here, which makes isopropyl higher priority than that. The final third rule is that, the third sub-rule is that if we have double bonds, or triple bonds, they're treated as if each were bonded to a separate atom. This is not immediately obvious, but in an example it becomes very apparent. So if we have CH2 group, then we expand this to a hypothetical group where we keep all these things together. But now the former double bond, we just add 2 more carbons, 1 carbon to each carbon. And we don't add any substitution to these carbons because they're sort of fictitious carbons anyway. And now we look at the priority, how will this group rank in priority? And we often refer to the second rule in this case to establish its priority in the sequence. If we have a cyano group, for example, then this would translate into carbon, which now all 3 bonds to nitrogen are expanded, and there are here 2 more bonds to carbon. Okay? Now these things, these rules, they appear a little confusing now, but they're actually very simple. So just practice them on many examples, and they really will very soon appear very, very routine. The second part, so this whole thing was the first big rule, which had 3 sub-rules. The second rule is a little more difficult to visualize. So what I often see is that the first rule is very easy, and the second one is a little more challenging. But the second one is actually really assisted by use of models. And so the second rule will be that you rotate your molecule so that substituent 4, so the lowest priority substituent, points to the back. Okay? It's an example of how that is done. If we have our CH3, fluorine here, then our lowest priority substituent is this methyl group. Okay, and then we're going to rotate around this axis first to get to conformation, which is not often seen, but it's perfectly reasonable, because if you think about it, then we're going to move this fluorine to the left, but it will still be in the front, and bring this chlorine to the front while moving simultaneously the methyl group towards the back and between these. Now we're going to look at a different axis and turn this a little bit along this way to get to the conformation where now ethyl group comes in front of the plane. The methyl group is right behind this carbon, but I'll point it as if it isn't so that you can see it. And fluorine and chlorine are here now. So this is the tricky part. And this, if you practice with models, will soon become relatively simple, but now it certainly seems challenging. Okay, so now we reached our conformation with substituent 4 in the back. Then we reintroduce the numbers to other substituents. And then draw an arrow which goes from 1 to 2 to 3. In this case, this arrow would look like this. And if in drawing this arrow, we go clockwise, then we will assign this carbon an R prefix. But if we go counterclockwise, as we didn't in this case, we will assign this carbon an S prefix. And these words come from Latin rectus and sinister, which mean left, right, and left. So now if we go back to our alanine example, we can simultaneously apply a series of these rules. So this is again alanine, and our priority number 1 will be nitrogen. Our priority number 4 will be hydrogen. And between our two carbon substituents, the COOH group will be expanded into COO, COH. And according to this, now it will have a higher priority than the methyl group because the first point of difference is this oxygen versus hydrogen in the methyl group. So this will be 3 and this will be 2. The neat thing about this specific conformation as a drawing it is that the hydrogen is already in the back. And so there's no need to rotate anything. We just look at the arrow, and the arrow in this case goes counterclockwise. So this would be an S-alanine. And this happens to be the naturally occurring enantiomer of alanine. The other enantiomer, which I'm going to draw out here, and you can practice looking at its conformation later, would be an R-alanine. And even though these two compounds seem very similar to each other, and they really indeed are, only S-alanine occurs in nature. R-alanine is an unnatural compound. And that is a theme that is often seen in naturally occurring ionic compounds. It's oftentimes one enantiomer exists in a huge excess, or pretty much as an exclusive enantiomer, while the other enantiomer cannot be found in nature and has to be synthesized. This is one of the relatively big unresolved mysteries in chemistry. How did we get to this enantiomer-enriched world, natural world that we live in now? And we'll talk a little bit more about these biological and optical properties of different enantiomers in the next section.